Good afternoon, everybody. This is Tom Brands. I'm Customer Marketing Manager with Honeywell. I'm happy to be here with Stromquist and Company. Today we're going to talk about SmartLine level gauge, particularly the guided wave radar. We're going to talk about applications. This is our agenda. We'll talk about, first of all, why measure level. Then we'll talk about how to measure level. We'll talk about different ways of measuring level besides just radar. So we know as advisors to our customers that we want to make sure that we're recommending the right solution, not necessarily a guided wave radar for each and every application. There may be other technologies that are better suited for those process conditions. We'll go through an overview of different technologies, compare the advantages and disadvantages. We'll look at process conditions and how they play into what works best. And then we'll look at radar level in particular. We'll do a review and we'll talk about the advantages, disadvantages, and that would be guided wave radar as well as the non-contacting. Finally, we'll talk about specific applications. We'll look at particular industries. Within those industries, where might somebody use guided wave? First question, why measure level? One might be for inventory tank gauging. This is a custody transfer kind of measurement, and if you look at this picture at the bottom right-hand corner, this is a terminal, pipeline terminal. So a pipeline company transports their product through the pipeline, and at the end of the pipeline is the terminal. That's where the product's stored before it's turned over to somebody else or sold to their customer. And that is a custody transfer point. Another way to think of it, it's a cash register. So they measure how much of their product is being transferred to the customer. So accuracy is very important. So there will be level gauges on the tanks at the terminal. There'll also be level gauges in the storage tanks on the ship for the customer who's buying the product. Again, accuracy is very important. There may be some sort of legal agreements determining how they'll measure how much product flows through. It could be flow meters, it could be level gauges, or a combination of both. There might be some sort of commercial arrangement. There may be some local certification. Maybe the local government agencies require certain types of measurements, certain types of accuracy. And when we're talking about inventory tank gauging, we're talking about accuracies of plus or minus 1 millimeter. Remember when we talked about our level gauge, we're talking about plus or minus 3 millimeters for process kind of application. So here we're looking for plus or minus 1 millimeter. And to get that, we'll do some sort of pressure and temperature compensation. And these devices are typically, when it comes to radar level, these are typically 4-wire devices, meaning there's 2 wires for power and 2 wires for signal. Our process gauge is going to be a 2-wire device. And these are typically more expensive than our process gauge. So because accuracy is so important, people are going to pay a little bit more. They're higher performance. These work at terminals, and it's often our sister company, NRAF, who provides these inventory tank gauging. So that's really not going to be our concern with the process gauge. That's a different kind of level measurement. So for what we've been talking about, it's mainly about the process industry. And for the process industry, 3 to 5 millimeter accuracy is good. It may be for control purposes that they measure level, could be for safety, environmental, and for storage as well. Inventory and allocation. So this is as opposed to custody transfer where products changing hands. In inventory allocation, I'm thinking of like a big plant, maybe a big refinery that has different units, and they're trying to account for how much inventory is in a particular unit, and when the product moves from one unit to the other, they want to be able to account for it, to allocate it. So allocation means really keeping track of what product is in what unit and transfers and so forth. So it's important to be accurate, but it doesn't need to be quite as accurate as, say, the inventory tank gauging. And level, if we know the level within a tank, if we know the shape of the tank, we can convert that into volume. And if you know the density of the material that's in there, you can convert that volume into mass. And finally, you can use level to determine flow, if you know the amount of time it takes to move a certain volume. So there are a lot of different ways to measure level, and we want to understand these different ways, and when it comes to advising our customers is being sure that we're advising the right sort of solution to their level problem. So I've listed 7 here. There are certainly more ways to do it, and I've highlighted 5 of these, and that's what we're going to talk about in this next section of the presentation. We'll talk about these, what their pros and cons are, and when you might use one and when you might avoid using these technologies, how they work. The first is a capacitance level gauge, and this works off the idea of capacitance, and that capacitance is a measure of how much energy a body can store. And a capacitor typically is two plates that are kept apart at some distance, and they have a dielectric material in between them. So energy can be stored in this capacitor, and to get the amount of capacitance, you can see that equation. There's this K, which is the dielectric constant, the area, and then the distance between the plates. So the way we make a capacitor in a tank is to say that the rod of the capacitance probe is one plate, and the tank wall is the other plate. So with nothing in the tank, there's really no capacitance. But as you fill that tank up with the material has some sort of dielectric constant. That is what increases the capacitance. So as the level changes, the capacitance changes. So that's how capacitance level gauges work. So advantages, disadvantages. Advantages, they're easy to install. They can be mounted on the top or on the outside, and they're not really affected by changes in density or pressure necessarily. They don't really have the dead zone we talked about at the top end of the measurement. They're cost effective, fairly rugged, and they're not real sensitive to buildup and coating for conductive liquids. The disadvantage is that they're directly sensitive to changes in the dielectric constant. So when you're making this measurement, you're assuming that this material has a certain dielectric constant, and it's not going to change, because if the dielectric constant changes, all bets are off. And it could change with temperature. So temperature fluctuations can change the dielectric constant, and that will affect the reading. It can be affected by obstacles in the tank that give you a false reading. And it often requires an on-site calibration. So somebody has to come in there with an empty tank and say, this is 0 level, and then fill it up and say, this is 100% level, which is not real convenient to do. It's not real accurate, but they're not real expensive either. So industry is an example. Water treatment. This is a good example, a good application for capacitance. So if somebody doesn't require a lot of accuracy, they don't have a lot of money to spend on this measurement, it's not critical, capacitance might be a good measurement for them, as long as their dielectric constant is constant. Okay, the next one is using pressure to measure level. In this case, we're using differential pressure. And if you look over here, we're showing a differential pressure transmitter. One side is connected to the bottom of the tank, the other side is connected to the top, and this is using impulse lines, so we're measuring the pressure directly. And it really just works off this idea of hydrostatic pressure. And we all understand when you're in a swimming pool, of course when you go underwater, just at the surface, you don't feel much pressure in your ears, but the deeper you go, the more pressure you feel on your ears, because there's more liquid above you that's creating that pressure. And that's what's happening here, is as the level increases, there's more pressure being exerted by the weight of that fluid, and the differential pressure transmitter measures that. Another way to do that is to use these capillaries. These are filled with typically a silicone oil and remote seals, measuring the high side and the low side. Same idea, as the level changes, the differential pressure changes. The assumption here, though, is that whatever the density is, so advantages of this is there's no dead zones. It's not affected by turbulence, any kind of surface conditions. Foam doesn't matter. We don't have those things to worry about. And fairly easy to calibrate. The big disadvantage is that it's sensitive to changes in density. So you really need to have a constant density for this to work, because you're assuming that density is a certain value and it's going to stay that way. It can be sensitive to buildup, hardening on the capillaries. And if you have, not buildup on the capillaries, but on the diaphragms. And if you are using capillaries, those can be sensitive to temperature variation. So those big capillaries that I was talking about can be affected by things like just the sunshine. So sunlight will warm up that fluid and cause it to expand, and that can create errors. There can be some chemical resistance restrictions on the membranes, and this is a bottom installation. What I mean here is that if somebody says, hey, I want to make a reading on this tank, a level reading on this tank, the customer is going to have to empty the tank to install the pressure diaphragm at the bottom. So it's not always convenient to have to empty out a tank. And you can see all the various industries. A lot of people use this. This is a pretty common way to measure level. It has its pros and cons like anything else. The next technology is ultrasonic. So for an ultrasonic level gauge, it's similar in a sense to what we've been talking about with radar, but instead of a radar signal, it's sending out a sound wave. So it's an ultrasonic sound pulse that's being emitted. That's sent out and is bounced off of the surface. It comes back up. In this case, we measure how long it takes for it to bounce off the surface, and we assume the speed of sound in air, or whatever the vapor is that it's traveling through. So it has to have a medium like air to travel through. Sound will not travel in a vacuum. So it's independent of product properties, so if the dielectric changes or the density changes, it doesn't matter. Ultrasonic can still measure it. It's not in contact with the process. So with our waveguide, we've got to be careful in case there's a corrosive kind of environment. We don't have any contact with ultrasonic. No site calibration required. However, it can be sensitive to things like turbulent surfaces and foam. And really, probably the most important thing to know is that you've got to have certain conditions with the vapor space, is that there has to be a minimum amount of pressure, and we're saying here a minimum of 50 millibar for you to even make a reading. It does have blocking distance concerns at the top and the bottom, and it's really not used in high temperature, high pressure applications. Can't really be above 3 bar. So if the properties of that air that you're sending the sound wave through, if that changes, different densities, different temperatures, different pressures, that can cause a problem. But the industries and examples, again, water basins where you don't want to spend a lot of money making this sort of measurement. You don't need a lot of accuracies. And if that air is going to be fairly constant, the properties of that air, then it's okay. Displacer, this is another measurement. We talked a little bit about this earlier this morning, but what we're doing is using a bypass. Almost all the time, not all the time, but almost all the time, displacers will be mounted in a bypass. And the level in the bypass is going to be the same level as in the tank. We're making that measurement there. And that's a good way to isolate the measurement from any sort of turbulence or disturbances in the tank. But the way this works is off a buoyant force. So if we're kind of like measuring the weight of that float that's in there. That's a float that's right in the middle. It's on the end of a line. And if there's no fluid in the tank, it's just going to be hanging there, and it'll simply be the weight of that float. But as you add liquid to it, it helps to sort of float it, becomes more buoyant, it pushes it up, that force becomes less. So we measure less force as the level rises. This one is another one that assumes that the density is going to be constant. Okay? Now you'd think that float moves around a lot, but really it doesn't. It's just being moved up by the buoyant force, and it's just a slight movement. Advantages, disadvantages. The advantage, there's no dead zone. It's not affected by surface conditions or obstacles. Pretty easy to calibrate. But the concerns would be with variations in density. So this is another one that's set up around density. It's got to be what the assumed value is. And it's a mechanical device, so it's susceptible to buildup and hardening, and over time you get this mechanical wear and tear, and that affects the calibration, affects the accuracy of the reading. This one's also a bottom installation, and it's fairly common in some food, pharmaceutical, chemicals kind of applications, reactors in chemical plants, also refineries. Pretty common one is across a distillation column, is measuring the level within those trays on distillation columns. Our next technology is radar again, but it's non-contacting. So there's a couple different ways to do this. We have the antenna, and you can use a continuous wave, and that continuous wave just changes frequencies, and we use that. That's a different technology we really won't talk about today. But that's one way to do it, with the continuous wave. The other way is with an impulse. and we're going to use the impulse method. So this is saying no waveguide, we're going to send this pulse out, and we're going to see how long it takes to go to the surface and bounce back up without the waveguide. Same idea as what we talked about this morning. Now the advantage, one of the big advantages is that it's not contacting. We don't have to worry about a waveguide coming in contact with impellers or agitators. It is not going to come in contact with corrosive environments necessarily. And it's independent of the product density, so it's going to bounce off the surface no matter what the density is, as long as there's a change in dielectric. It can be a little more sensitive to foam than, say, guided wave radar, turbulent conditions, and you can get buildup on the antenna. So if there's a product that you're storing in a tank and there's some vapors that come off of it, if the vapors condense on the antenna, that will cause a problem. That'll block the signal coming out. This morning we talked about how we want to send the pulse right down the waveguide, and we want it to reflect right back up. Well, we've got that waveguide to guide it normally with our guided wave radar, but with the non-contacting, the wave is going to tend to go out to the side. Okay? And we want it to be as focused as possible, but inevitably it's going to go off to the side. It may bounce off the tank wall, from the tank wall go off the surface and come back up again. We'll get multiple reflections, and these multiple reflections can be a problem when it comes to sensing or determining what is actually the surface reflection. And it does, it has the same issues with blocking distance at the top and the bottom. And these are the different frequencies. We mentioned this a little bit before, is that the non-contacting will have temperature options. The 6 gigahertz versus the 26 gigahertz. The lower frequency, the 6 gigahertz, will do a better job of penetrating foam. However, it's going to be spread out a little bit more. The 26, on the other hand, is going to be more sensitive to foam, and it's going to be a narrower focus. So it kind of depends on the application which way to go with those. Some application examples. It might be a process tank that has strong currents, fast changes in pressure and temperature. So when we're looking at a guided wave radar, we were concerned about pulling forces, forces against the side, and so forth. If there are too many forces that are pulling or acting on the waveguide, this is a good application for non-contacting. We talked about being able to measure solids too. Sometimes it's better just to use a non-contacting radar just for those concerns with pulling forces. Slop oil tanks, this is for the recovery of hydrocarbons that have variable compositions, because if the density is changing a lot, you can't use some of these other things like displacers, you can't use differential pressure. And a slop oil tank, this is kind of interesting, is when a company is pumping a product, let's say it's a liquid, and it's liquid A, it's going through the pipeline and it's going to go into storage tank A. That happens, they pump product A, it goes into storage tank A, and then they want to pump product B over to storage tank B. Well, they don't just pump A and then stop and clean out the pipeline and pump B. They put one right behind the other, and there's sort of this rag layer between the two. It's kind of a mixture of product A and B, and they call that that goes into the slop oil tank, and it's not really something they can sell, but they don't really know what the density is. So radar is a good way to measure a product with an undetermined density. Could be in separators, and these work well in these plastic fiberglass tanks, the non-conductive ones that we had mentioned. So let's talk about TDR as a review. This is the time domain reflectometry, the principle that we use for guided wave radar, and we're going to be talking about guided wave radar now in its applications. So we said before that we're going to generate these electromagnetic pulses. They're going to be sent down a waveguide. They're going to bounce off a surface and come back. We measure the time it takes for it to go there and back and get a distance from it. And whatever the probe length is, that's the measurement range. And we talked about a reflection that occurs when there's a change in dielectric. So water has a high dielectric of 80, air has a dielectric of 1, so you get a nice reflection off of water. And then the dielectrics we've seen as the values decrease, and the limit there is 1.4. Our radar is sending out a pulse. It looks like this. This is an echo curve, and we're getting the reflection at the surface. Sometimes people are using just the positive peak. It's not a very high peak, and what we're doing with ours is using the bipolar to get a higher peak-to-peak voltage with the just a bit better signal strength so that we can pick the signal out as opposed to noise. So when we send the signal out, some of it is reflected and some of it carries on, travels through further to maybe for another reflection. But if there's a very small difference in dielectric between the vapor and the liquid, we're going to get a small reflection. On the other hand, if there's a big difference in dielectric, we get a strong reflection. Now, generally, when you'd want to use guided wave radar, applications where you have a density variation, and there's fluctuations in pressure and temperature, even high pressures and temperature, for long measurement ranges. We can go to 150 feet with a cable on guided wave. And maybe working through a narrow setting. So let's say there's a lot of stuff inside of a tank. The guided wave with a stilling well or with a coax can work over a narrow range. It's not going to be affected by obstacles that are in the tank. Guided wave is also very good for interface measurement. These other technologies really don't work so well for interface. You can do interface measurement with differential pressure, with the capacitance type, but it just doesn't work quite as well. In the case of differential pressure, you have to maintain a certain height in your tank, the surface height, to measure the interface. So if that height remains the same, then the interface between the two liquids changes, and you can measure that. But to be able to do that, this surface level has to be kept the same, and that's not always easy to do. With guided wave, you don't have to worry about keeping that surface the same. Disadvantage is this does come in contact with the process. There can be issues with pulling forces, with corrosion, and buildup. The mounting can be just simple, like we're showing here on the left. It can be with the stilling well to sort of calm the surface and focus the wave. And then we talked about a bypass too. This gives us isolation from the process, gives a nice calm surface too. The different probe selections, we have the wire type probe, which is going to be used in most applications, will go up to 150 feet. The single rod probe, and this would be segmented, and this will go out to about 30 feet in length. And in either case, we have to be concerned about the forces going from side to side, as well as the ones that are pulling on the probe. Coax probes give us nice focused signal, but we have to make sure those are in clean kind of applications. Twin probes, same thing. That's going to focus the energy between the two, either cables or the rigid probes. And here's a comparison. And really what I want to highlight is with the coax, we want to make sure that it's a clean liquid. We're not going to have problems with bridging. And then on the single wire, what we're saying is that for tall, narrow wells, you want to be careful with a single wire. So why do you think that would be? So let's say it's a long well going down there. You've got a cable probe down there with the weight on the end of it. What might be a concern with that? Exactly. So that would move within the stilling well, and wherever that cable touches the wall of the stilling well, you're going to get a reflection, and that's not going to be the reflection off the surface. Now, specific industries, power generation. I've listed some here. If you have other ones to contribute, please chime in. But on cooling tower basins, boiler feed water heater, the steam boiler level measurement. Now, this would be in a bypass, and the boiler level is going to be high temperature, high pressure, and that's not our first release. That will be a subsequent release of the product. Blowdown sumps. And here's a particular application we're looking at. This is the low pressure preheater. Some people call this a feed water heater. So in a power plant, what they're doing is heating up the water before it goes into the main boiler. And it's going through different stages called feed water heaters. And in each stage, the water is getting hotter and hotter, and it's being heated up by steam. Now that steam that's being used to heat it up will condense, and we're trying to measure the level of that condensed water in one of those stages. So it's the condensation, extraction of steam, and low pressure feed water heater. The dielectric constant is 1.4 to 2. And remember, we'd said that the dielectric constant of water is 80. The reason it's so low in this application is because this water is aerated. There's a lot of air bubbles in there. That lowers the dielectric constant. So that makes it a challenging kind of application. Tank height 6 feet. This is going to require a special probe and special software, which is coming out in future releases for our guided wave radar. So special probe, special software, if you're going to do something with an aerated kind of liquid like water. Okay. Chemical industry, reactor levels, chemical storage tanks. So I've listed a bunch of different chemicals and their dielectric constants. And we're talking about applications in the bottoms of a stripper or rectification column. There's distillation columns. They're often measuring the level on the trays, across the trays in distillation column. Reflux drums, small tanks for additives, product separators, and so forth. Oops. And here's a look at a specific application. This is in an ethylene plant on a quench tank. In this application, there's a combination of gasoline and water in a tank, and they want to measure the surface and they want to measure the interface, and they're going to use a bypass. And guided wave works real well in the bypass. It's going to measure the level of at the top. So it's gasoline and water. Gasoline is going to be floating on the top, water's on the bottom, so they're measuring that level. Then they measure the interface between the gasoline and the water, and they're able to control based off of that. Again, done in a bypass. And this will be a single rod mount. Another petrochem industry, this is measuring solids or pellets, and this would be polyethylene or polypropylene granules in a silo, dielectric constant of about 2. So this is solids. The temperature is not a problem, the tank height's fine, but we would typically use a single rope probe, and that would be anchored at the bottom. But remember, the solids kind of application, the product for the solids application is not available now, and that is of April 2015. That's not in this release. Now, I'm talking about oil and gas downstream here. Specifically, that would be refineries. So it could be feed tanks, interface in a scrubber separator, the distillation column we've mentioned in the chemical industry too, across the trays, the water condensation, the gas condensation tanks, the flare knockout drums. So these flare knockout drums would be on a flare line. So where they're trying to flare off some waste product, it's typically a gas. It's going to go through a line before it goes to the flare to be burned. And you'll get condensation, and that'll be collected in these pots, or just sort of collection tanks. And so what they'll do is they'll measure the level in these pots, and as the level gets too high, they'll want to drain it. So they'll monitor that level to know when to drain the flare knockout drums. Continuing with refineries, the desalter is really the first stage as the crude oil comes into the refinery. So it's pretty, I mean, it's got some sand in it, some water, some oil, and there's a little bit of separation that still needs to happen. And the desalter can be kind of a challenging application, but it's good for guided wave because the density is kind of variable. It's not well known, but there can be some concern with emulsification there. This is in the refinery. There's an application on liquid paraffins. So refinery is just taking this crude oil and breaking out into all the components like gasoline and kerosene and propane and so forth. And one of them is this liquid paraffin, or sometimes called mineral oil. And its dielectric constant is around 2, which is good. The temperature, the tank height, all those things are good. And it's a good application for guided wave. And since although the dielectric constant is fairly low, it's not too low to measure. Moving upstream and midstream, so this would be pipelines and at the well sites. Often for these light end hydrocarbons like freon, butane, and ethylene, their dielectric constants are low. So we'd want to be careful when we're getting down to the 1.4 area, but this is one we just want to approach with caution. Storage tanks, mud pits. These are mud pits are used on drilling rigs. The level and interface measurements on separators. This is another kind of application at the well site. Fuel storage tanks and the production tanks. Production tanks, that was one of the examples we used in the application validation toolkit. So one of the requirements from the in the U.S. is that producers would measure the level in their production tanks to prevent overfill. So the overfill might cause environmental damage. For that reason, the government requires that they have to make this level measurement. So that's a good one for us. Steel and mining, I've listed some various applications. Ore measurement in bunkers, the fill height measurement in converters, ore crusher in the mines, storage of coarse bulk materials. Of course, in all these cases, you'll have to be careful for pulling forces. It might even be better to go with a non-contacting radar. The cement and clinker levels, pulp and paper, pulp levels. It could be the wood chips. Again, another solids application for level. Water trap in a paper machine, and so forth. Water applications for wastewater digester tanks. The second one is open channel flow. So this is if you have a very big body of water and say you're flowing it from one area to another, you're going to go through something called a weir or a flume, open channel flow measurement. And as you're going through this weir or flume, you're measuring the level across the notch. And as that level changes, that changes with flow. So if you measure the level across this notch, that can give you flow. This is often done with ultrasonic, and I think we really want to note this can be done with radar, but because ultrasonic has traditionally been the way to do it, and that's most often what people will do. Other applications, compressor, wet seal oil pots, hydraulic oil. And then here's another application, and this is called animal rendering or tallow oil. So what this customer is doing in Vancouver is taking the animal byproducts, the food byproduct from the area, butcher shops and grocery stores, the things that are not edible, and taking that and processing it to get the oil. And that oil is used for, I guess, perfume and makeup and making candles. And in this case, our gauge is being used to measure the level of that tallow oil as it's being stored. So fortunately, I went to visit this one in the wintertime. And here's a look at an echo curve. So this is actually the output from there. And this is the flange reflection and then the reflection at the surface. So not a common application, but that's one that works. And I'm going to put this, take a quick look at this ammonia application, just to say that ammonia is something that we can do, but it's one that we want to approach with caution. It has a low dielectric, and then ammonia is just tricky in general, I think really because it absorbs some of the microwave energy. So it's something we can do. It's probably not something we'd want to do for really a long measurement range, but sort of looking at the application, it's something we would consider. Interface measurement. You can do interface measurement with differential pressure, but we said you have to keep that top surface level the same as the interface between the two changes. Okay? Same thing with capacitance. If you keep that top surface level constant, then you can monitor the change in interface between the two liquids. Guided wave, on the other hand, it doesn't matter. You can still raise and lower the surface while the interface between the two changes. So really guided wave is the best way to do interface measurement if that's something that the customer needs to do. And here's a table that sort of compares and contrasts the different technologies we talked about: guided wave radar, capacitance, ultrasonic, the displacer, and differential pressure. So they have different ranges. The guided wave will go up to 50 meters. And different pressures. So ultrasonic is not going to work in real high pressures, temperature variations and things, and different accuracies. So really, what I want to show here is that There's a lot of different ways to measure level. There's pros and cons to each one, and these are just things to keep in mind when you're advising your customers. So, and as a summary, why use guided wave radar? What applications? It's really good for unstable process conditions where viscosity, temperature are changing quite a bit, or density is changing. Where you have agitated surfaces, guided wave works well when compared to non-contacting radar or maybe ultrasonic. Works in high temperatures and pressures. We know that some technologies have a limitation with that. And it will work with fine powders, sticky fluids. It can work with solids. Sometimes non-contacting is a better way to do it, but it's a matter of just really evaluating the application. Interface detection, this is really the best way to go with guided wave. And finally, it meets the process industry requirements for loop power or low power kind of devices. So we talked about why measure level, inventory tank gauging versus process, different ways to do it, what the advantages, disadvantages of each one was, process conditions, and we reviewed the different industries and particular applications within each one. So that concludes this presentation.